Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss some problems on module 4 in question bank. So the module 4 is digital modulation techniques. Digital modulation techniques. So we know the digital modulation techniques, that is ASK, PSK, FSK, DPSK, QPSK. So that are common. So this module is corresponding to the analog and digital communications course. So now we are going to discuss analog and digital communications course question bank of module 4. Okay. So what is module 4? So module 4 belongs to the digital modulation techniques, and these digital modulation techniques are covered by 4th course outcome. So what the 4th course outcome states: analyze digital passband communication schemes ASK, PSK, FSK using modulation and demodulation process. Okay, so this is the course outcome. Now we are in the part A. What is part A? Part A is the problem solving and critical thinking questions. So here we are using that formulas and apply and some critical solving questions. Okay. So coming to the first problem, the bit string 11011000101 is to be transmitted using DPSK signal. Determine the encode sequence and transmit phase sequence. So for this DPSK signal, we must know what is the reference bit using. Which reference bit is using? Why? One reference bit must be required to solve this problem. So that reference bit may be either 1 or 0. Okay. So in this problem, I am considering 1 as the reference bit. Here they are not given any bit. So I am using 1 bit. Again, in this session, another problem is there in this presentation. So at that time I am using 0. For this time I am using only 1 as the reference bit. Okay. So for 1 as a reference bit, we have some procedure. Okay. So at that time we know the procedure. When you are going to solve it, then I will reveal this. Okay. So first you go to write the given input sequence. 1 1 0 1 1 1 00 1 0 1. Okay. Here I am taking 1 as the reference bit. So 1 as the reference bit. So dk minus 1 is required. So when you're taking 1 as a reference bit, that first bit as usual taken as 1. Okay. So how dk minus 1 is produced? So dk minus 1 is produced by taking OR operation in between the bk. So in between bk is the given input bit stream. So in that bit stream we are going to operate OR operation. Okay. So here 1 or 1. So OR operation. So we got 1 1 0 1 0 1 1 1 1 1, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1. So this is my OR operation. In between BK bits, I am going to generate DK minus 1. Okay. Next, the phase of DK minus 1. Here, when considering the phase, here we are having only 2 bits. That is either 1 or 0. So here I am considering for 1 bit as in 0 phase. For 0 bit, I am considering pi phase. So 0, 0. Okay. So dk is equal to bk XOR dk minus 1 complement. Understand? Here my dk is complement of module to sum of bk and dk minus 1. So here I am considering. Okay. So what you got? 1, 1. So 1 XOR 1 gives 0. But complement is there. So it is 1. Okay. Again 1. So 0, 1. 1 comes. But complement is 0. 1. 1. 0. Okay. So 0, 0. 0, 0 complement is 1. 1, 1. 1. 0, 1. 0. 1, 1. 1. So this is my dk. So dk is nothing but the complement of XOR operation between bk and dk minus 1. Okay. So this is my dk. Now phase of dk. So same for 0. For 1. 0, 0, pi, 0, 0, 0, pi, 0, 0, pi, 0. Now phase comparison. Phase comparison between dk minus 1 and dk. So after comparison of these two, we are getting the original bit sequence once again. So here this is my phases 0, 0. There is any phase change? No. So no phase change gives 1. Again no phase change 1. Here phase is changed 0. Here no phase change. Here no phase change. Here again no phase change. Here phase change. So 0. Again phase change 0. Again no phase change 1. Phase change 0. No phase change 1. So once you go to check similar what you got. Similarly you get same bk is what you produce one. Understand? So coming to the second one, determine the baud and minimum bandwidth necessary to pass a 10 kbps binary signal using amplitude shift keying ASK. For ASK, n is equal to 1. N means number of bits you can set. Only 1 bit at a time. So n equal to 1. And the baud and minimum bandwidth are determined from bandwidth is equal to 10,000 by 1. So simply 10,000. Again baud is equal to 10,000 by 1. Also 10,000. So the use of amplitude modulus carrier amplitude modulated analog carriers to transport digital information is a relatively low quality and low cost type of digital modulation. Okay, and again very low speed telemetry circuits. So this is the application of ASK. Okay, so very simple. The bar and minimum bandwidth, okay, divided by n, 10 kbps by 1. Okay. So third one, determine the peak frequency deviation, minimum bandwidth, and bar for a binary FSK signal with a mark frequency 49 kHz and a space frequency of 51 kilo and an input bit frequency of 2 kbps. Okay. So in FSK, binary 1 is represented with a high frequency carrier signal and binary 0 with a low carrier frequency. So why? Because here, for example, this is 1, 0, 1. So how to represent with this one, like this. So this is a high frequency signal. Symbol 1 is represented with a high frequency carrier signal and binary 0 is represented with a low carrier. So the shift is the frequency differentiation between the mark and space signals. Okay. So the deviation is also equal to 1/2 of the shift. So Fs minus Fm is equal to 2 delta F. So here they given what is the space and what is the mark. Space is 51 kHz and mark is a 49 kHz. Input bit rate is 2. Okay. So delta F is equal to Fs minus Fm. 51 minus 49, 2 divided by 2. So delta F is the 1 kHz. The bandwidth of FSK signal is Fs minus Fm plus 2 by Tb. So Fs space mark 51 minus 49, again 2 plus 2 by Tb. So Tb, you can move this one as Rb. So 2 Rb. So that's why Fs minus Fm plus 2 Rb you can write. So here 51 minus 49 plus 2 into 2. So 2 plus 4 is 6 kilohertz. So this is my answer. Okay. Now the fourth one. Assume that 36,000 bits per second data is sent over a passband channel by frequency shift keying signaling scheme. Estimate the transmission bandwidth. So the bandwidth is equal to 4 FB. Okay. So 4 into 36,000. That is equal to 14,400 hertz is nothing but 14.4 kilohertz. So my bandwidth is 14.4 kilohertz. Now the sixth one, a voice signal is sampled at the rate of 5,000 samples per second and each sample is encoded into 5 bits using PCM system. The PCM data is transmitted through a baseband channel via 4-level palm pulse amplitude modulation. Determine the bandwidth of the modulated signal. Okay. So first write the given data. Fs equal to 5 kHz, N is 5 bits and level of PAM is 4. So these data we are going to enter. Then the required formulas. Bandwidth is equal to Rb by 2 log 2 M. So Rb is NFS, already we know. So NFS divided by 2 log 2 M. M place is 4. So N is 5 into 5000. So 25 kilo divided by this 4. So here 5 into 5 divided by 2 into 2 log 2. So 25 by 4. So 6.3 kilohertz. So that is the bandwidth. Okay. Next, seventh one. You have an FSK transmitter using a carrier of 500 kHz, sending 10 kbps and a frequency deviation of 100 kHz. How much bandwidth do you have need for your transmission? Very simple. So bandwidth is equal to 2 delta f plus RB. Okay. So the frequency deviation is 100 kilo. So 100 into RB. So 100 kilo. This is 100 kilo plus RB. So 10 kbps. So RB is 10 kbps. Okay. So the bandwidth is 220 kilohertz. 220 kilohertz. Okay. So it's a single bit problem. Now assume that 4800 bits per second or 4800 bits per second random data are sent over bandpass channel by using the following schemes: BPSK, BFSK. Determine the transmission bandwidth. So what is the BPSK bandwidth? It is nothing but 2FB. 2FB. So 2 into 48,000, it gives 9.6 kilohertz. Whereas FSK, the bandwidth is 4FB. So 4 into 48,000. So it is 19.2 kilohertz. Okay. So when you know the bandwidths of BPSK, BFSK, you can easily find the answer. Okay. Yeah. Another bit stream. So now for this bit stream, we are going to find this bit stream using 0 as the reference bit. Okay, 0 as the reference bit. So here I am writing BK is 1, 1, 0, 1, again 0, 1, 0, 1, 0, double 1. So this is the given bit sequence. So now I am going to find dk minus 1 using 0 as the reference bit. So for the first bit taken as similar as 0. Now what the operation? So the dk minus 1 is produced using the complement of R operation. Whereas in 1 we are taking the R operation, but here complement of R. So 1, 1. Actually for R operation it is 1, but complement of R, so it is 0. Again 1, 0, complement 0, 0, 1, 0. Similar, you get all zeros. That is the dk minus 1. Now phase of dk minus 1. This is the phase of dk minus 1. So what you said? We follow 1. 1 having 0 phase and 0 having pi phase. Okay. So all pi's. All pi's. Okay. Next dk. We are going to find the dk. So what is dk? dk is complement of XR. Complement of XOR operation between BK and DK minus 1. Okay. So having 1, 0. So for this 1 0. So 1 0 you got 1. But the complement, it is 0. Again 1 0 1 but 0. 0 0, it is 0 but complement is 1. But complement is 1. Same 1 0. 1 0 is 1 but complement is 0. Similar 1 0 0 0 0 1 1 0 0 0 0 1 1 0 0 again 1 0 0. Okay. Now phase of decay. So for where 0 is located, you taken as pi as phase. 0 pi 0 0 pi 0 pi pi. Now phase comparison. Now phase comparison. By comparing the phase at the receiver, you are going to identify which one is. Understand? Here BK is the input. So we are going to send this BK sequence using this DPSK. Okay, differential phase shift keying. So the receiver is identified which bit sequence is sent. Okay. So now I am going to compare this. So there is any phase change? No. Without phase change, you can take it as 1. Phase change 0. 1 0. So 0. No phase change 1. Phase change 0. No phase change. So similar will get. Okay. So here 0 1 0 1. Yeah, here 0 is missing. So but 0 it is phase. Yes. Zero. This one. Yes. This is the required sequence what you said. Okay. I hope you understand well. So the last one is for a BPSK modulator with a carrier frequency of 70 MHz and an input bit rate of 10 Mbps megabits per second. Determine the maximum and minimum upper and lower sideband frequencies. Draw the spectrum. Determine the minimum Nyquist bandwidth and calculate the baud rate. So given RB is 10 Mbps, FC is 70 MHz frequency. So this is a BPSK modulator. Okay. Yes. Maximum upper sideband frequency is FC plus RB by 2. So FC is the carrier frequency 70 MHz. RB is bitrate is 10. So 10 by 2. So 75 MHz. So this is the 75 MHz. And maximum lower sideband frequencies. So FC minus RB by 2. So 70 minus 5, 65 we got. Okay. So this is the frequency spectrum. Okay, very simple problem. Draw the spectrum, determine the whatever the upper sideband, lower sideband frequencies. Okay. So for the development of this content, we use Simon Hackey and Sanjay Sharma, Jas Chitodi, and some books. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.